Last one, the Circumcenter method for the variational inequality problem. And in the last talk, we introduced one-step approximate method, and it's for the variational inequality problems with some assumptions of the operator f, and there are some applications of the variational inequality problems. For example, if the operator equals to the gradient of the subgradient, it could become the convex optimization, and if the C equals to the positive of the Rn, and it could be the nonlinear complementary problem. And okay, so the projection method which we introduced before, it can be interpreted as a kind of a projection gradient method. If this t here equals to the gradient, but in this case, the assumption is very strong. We require the t is strongly monotone. And also, if without line search, we also require the Lipschitz continuity. So it would be a very strong assumption for this method. And yeah, we have some definition of the different kind of monotonicity. And the strongest one is strongly monotone, and the most general is monotone. So we will introduce a method for the paramonotone, which is weaker than the strongly monotone, and the definition is here. We have some examples for the paramonotone. If T is a subdifferential of the convex function, T is paramonotone. And also we have if a matrix, if T is a fan operator, if the A is the positive semi-definite but not necessarily symmetric, this T could also be paramonotone. In this case, we can use some other methods which do not require the strongly monotone assumption. Okay, the first method is by the Fukushima, which we use not exact projection, but inexact projection here, CK. CK is a half space defined by the VK. VK belongs to the subdifferential of the GK here. But the drawbacks of this method is still the strongly monotonicity. So this is a proof. But Union and Alfredo proposed another one. Two versions. The first version is with exact projection, and but for this method they didn't require the strongly monotone anymore, just the paramonotone. So it's a kind of improvement. So they use the quasi-phasor monotone to prove the convergence. Okay, so this we have discussed before. And before. Yeah, this is a convergence result. We assume the T is maximum monotone and paramonotone, and the sequence generated by the method which we mentioned before, convergence to a solution in the solution side. But by the way, if the T here, sorry, there is typo here. If the F or T, if the operator is not strongly monotone, the solution side is not a unique point. There may be many solutions, but the sequence will converge to one of the solution point. Okay, this is a proof. I don't will introduce. The second version is that also for the paramonotone operators, but they will project to the CK. CK is the same as defined in the same way as it is in the Fukushima's method. It's a half space. Sorry, this is less than 0. So in this case, the projection is very cheap. We can project it to the this half space, and we have closed formula. So this is not new. So yeah, we also need some assumptions and assumptions. And this is a key lemma. The key lemma we can prove that the sequence is bounded. The sequence in the graphs, this UK belongs to TK. This is also bounded, and the distance between the xk and the set C is approaches 0, and the xk minus xk plus 1 is also 0, and then we can prove the other clustered point xk belongs to C. But the proof is somehow not, it's a little complicated, so I didn't put the proof here.
Excuse me, but you don't prove convergence of the sequence. You prove it
Sorry.
Convergence, in this setting you have convergence. No.
This one, yeah.
Yeah, you don't have.
Yeah. All the we only prove that all the class pointer belongs to the set belongs to the solution set. No. Sorry. The whole sequence approach convergence to some solution.
The solution is unique.
No.
It's there.
Yeah. If it is unique, it approaches the solution set. If it is not unique, all the clustered point will belong to the solution set. Okay, so second is the two steps projection method. The most classical one is the extragradient method. We have first we calculate the yk. We calculate the yk, and the second we calculate the xk plus 1. The convergence requires just a monotone and the Lipschitz continuity if we do not use any line search here. And yeah, this graph is for explain the extragradient. So we have xk here, and we give some step size tau or lambda, and we reach the point xk minus the tau fxk, and then we project back to yk. So here I want to say a little bit more about here. The motivation of extragradient method. Of course, it removes the strongly monotone. But why did we need this point yk? Because as long as this yk in paper U and Solodov, I will show the picture later. This yk gives a direction. You see, we get another point from xk. The direction is somehow fyk with some step size. Here is a constant step size. This gives us a new direction, and this direction somehow tell us how do we approach the solution site, which means this point could be the projections to some half space or hyperplanes which separate the xk and the solution site. This is very clear in the paper Binar with Solodov. I can show the, not this one. Yeah, let's see this here, this one here. First, we have the point xi here. This graph is actually we have discussed this before, but let's discuss this again. This xi is a current point, and first we do.
Move the mouse pointer because it's over. Yeah, move to the bottom of the page.
The mouse.
Yeah, the mouse.
Sorry, I didn't realize. It's okay now?
Yeah.
Okay, so if we have a point xi here, what do we do? we get first we get a new point xi, which, sorry, I get a little.
No, the first point you get is.
I write it here because I get
Yeah, that's the point. That's correct.
First we have xk, okay? Then we get a point
Bar xk.
sorry, how can I write it? Xk minus alpha f xk. And then we project, we get a point, the projection to the set C, xk minus alpha f xk. We call this point yk, okay? And then we want to get another point zk. Zk is somehow between the line segment of this xk and this we call yk, okay? But there you use the alpha equals to 1. Here we have alpha, but okay, we use the 1 here. We use the 1 here. So we want to get a point zk. Zk equals to the line segment. The line segment like 1 minus theta xk plus theta yk. So we have a point zk here. Zk is in the picture is zi, and then we construct a hyperplane hk. Okay, hk is defined by the w belongs to Rn, and the f zk and w minus, sorry, zk is less than 0. So we have this hk here, and what we do next? Actually, we can calculate the projection of xk to this hk. So we get this point, xk bar or xi bar, and then we project again. We project to the set C, the feasible set. So P, H, K, X, K. Actually, this equals to the P, C intersect with HK, XK. So this is the algorithms by Binary and Solodov. So in this case, the only thing, there is one thing we need to determine here. It's this theta. It determines the locations of this zi. It determines zi is closer to xi or closer to this projection. But how did they determine this theta in their paper? They used the Armijo search, which they use here. Zk equals to, sorry, how to see, how, 1 minus theta. No, it's not in this one. Sorry about that. Yeah, dk is defending xk minus gamma j and yk. So the line search j equals to, it's the smallest integral that satisfies f zk yk, no, this should be zk minus xk, and it's greater than some constant sigma. This should be zk minus xk square. This is a line search in this paper. This sigma belongs to 0 and 1, and this j is the smallest integral which satisfies this inequality. There is a good point of this kind of line search here. This guarantees that this hyperplane, actually in this picture is a hyperplane. This half space separates the xk and the solution side. So if we do the projection to this hyperplane first, and then we project to the intersection of this hyperplane with C, we can actually go approaches the solution side. So we can this kind of method is also a kind of two steps projection method, and this method has a good interpretation because we project from xk to the intersection of a half space which separates the solution side, and this point zi here, zi or zk here, gives us a direction which this fz, because this half space is defined by this point and this vector fz, and this fz gives us a direction which makes us can get approaches the solution side. So we go back. Sorry. So we go back to the extra. Not this extra gradient. Yeah, we go back to this extra gradient method. Why we calculate the yk here? Actually, this yk has the same, could be interpreted in the same way as the zk here, or zk, or zk here. It gives us a new direction. These directions can make us get approaches to the solution set, not only the set C, not only the feasible set here. But by the way, Professor, I just read this from a paper, but I cannot prove that the extra gradient method can be interpreted in these frameworks. Can you understand what I said?
I see. Well, because there's no immediate search in the.
Yeah.
So assume that sleep is continuous.
And
you choose the parameters so that not it's a little bit different, but because you project onto the intersection of a house space with the physical set. And here you.
Sorry, we go to your picture. Yeah, this picture is directly. I make a screenshot from the paper.
But the first point you compute is PC of xi minus f of xi.
This point, yeah. Okay.
This point.
Okay. And then we have this zk, but zk is determined by the line search. Your line search.
But if you have the Lipschitz constant of the operator. If the operator, that's correct. That's working. Okay. If the if your map is ellipsis continuous, if your operator f of x is ellipsis continuous, you can choose the step so that you don't need to do a backtracking.
Okay, yeah.
And then it will be more similar to Korpolevich method.
Yeah, but in that sense, if we know the big capital L, and we do not need to use backtracking.
Yeah.
But in that sense, maybe we cannot find a hyperplane which separates the solution set and the point.
Well, the condition that the stopping criterion for the Armigio search
Is this?
guarantees separation.
Yeah, guarantees separation.
So if you choose if you scale your operator so that has a ellipsis constant 1 or 1/2, I don't know, probably 1, then you don't need to do the backtracking. But even though it does not become Korpolevich, even though it's more similar to Korpolevich if you know the ellipse constant and do the step according to obviate the need for backtracking.
So it's a different kind of method, yeah? I mean, this method and the Korpolevich method.
It's different in the sense that even if you don't have do backtrack, you project onto intersection. You will not project onto this hyperplane and then project onto the set. We are projecting onto the intersection. So even it becomes closer to Korpolevich.
Okay. Okay, because in some papers, I will tell you later, not now, someone said the Korpolevich method can be interpreted as the projection. We go back to the Korpolevich. They said, not this one, they said this point can be regarded as the projection to some half space which separate the point xk and the solution site. But I have doubt about that because up to now I didn't find that half space. That half space could separate the point xk.
You have separation at the hyperplane which pass through yk and have the normal vector given by f of yk.
You mean we can have a hyperplane here?
Yeah, the hyperplane is there.
It's pass through the yk.
Yeah, that's
the normal vector is fyk.
Yeah. This is the hyperplane you are sure the solutions are. It separates xk from solution.
But not here, yeah. But not here. It's here, past yk and the.
Yeah, it passes over yk. This. Well, the drawing is not okay. Well, maybe it can be an over-relaxed projection.
Can be interpreted as an over-relaxed projection, yeah.
Yeah, but then you must check do the computation to see if you got it.
Okay. So this yk, you mean the projection, the hyperplane is here, yeah?
Yeah, the hyperplane is there.
And this is somehow fyk, is the normal vector of this half space.
You know that the solution is to the right of this hyperplane.
Okay. And this point, xk minus somehow, I use tau here.
No, but this drawing is not good because you are doing a over relaxation. Bigger than 1.
Yeah, it looks like over.
It's bigger than 2, and this does not guarantee convergence.
You mean somehow like here, yeah?
Yeah. You have, yeah.
But this is really the over relaxed projection or no?
You must check if the parameters of which you choose, because what do you know about the tau?
Tau is somehow belongs to the one, something like that. Okay, I will check this. I will check this now, because what I'm going now is because to interpret this method. This method is by Professor Olison and some other guys from Australia. To interpret this method, why they can use the approximate projection. Oh, sorry, inexact feasible projection here, because we need to somehow to interpret the proof of the extragradient method. But I will say it very fast. Okay, so we have xk plus 1 minus x star square. This x star belongs to the solution side of the I use t here and say is a solution point in the solution side of this variational inequality problem. And okay, so this is xk plus 1 here, and this is xk minus what I use? I can use lambda t. Sorry, I use f here, yk, and this point is xk minus lambda fxk, and this projection is yk is the projection of this point. And we have some solution, x star here, belongs to the solution side. I use f here. So first we can use the obtuse angle of these three points, because this xk star belongs to the solution side, and this xk is the exact projection of this point, xk minus lambda fyk. So this angle is obtuse. So it's obtuse triangular. So we can have the xk minus alpha fyk minus the x star. Sorry, this should be minus xk minus alpha fyk minus xk plus 1 square. Okay? So we can expand them, all of them, so we can have the xk plus 1 minus x star here, square. Sorry, and we can have xk minus xk plus 1 minus x nsk square plus 2 alpha fyk x star minus xk plus 1. Up to now, we just use the obtuse angle property here, and we want to eliminate the x star here. We use the property of the variational equality. So we can use f yk and x star minus xk plus 1. It's equals to fyk x star minus yk plus yk minus xk, and we can separate them, so we can have fyk and yk plus minus plus and we know that the x star is solution. X star belongs to the solution side of the variational equality. So we know this part is greater than 0. It's greater or less than 0. Yeah, it's less than 0. This one is, this part is less than 0. So this is less than the inner product of yk minus xk plus 1. So this inner product is less than this. Here we use the x star is the x star belongs to the solution set of fc. So if the point x star is a solution set, we can have fyk yk minus x star is greater than 0. This property is by the definition of variational equality and also the monotonicity. Okay, so this is less than xk minus x star square minus xk plus 1 minus xk square and plus 2 alpha fy, and this should be yk plus minus xk plus 1. So we do not have x star here anymore. And okay, so we can do some other, and we can add minus yk and plus yk here in this term. So we can have another one just to do this expandation. So we will have xk minus x star square minus xk plus 1 minus yk square minus yk minus xk square plus 2 xk minus alpha fyk and minus yk xk plus 1 minus yk. So we can have this, we can have this expandation here. So we need to analyze these terms. And here we can use that the xk, here we use xk plus 1 is a projection of xk minus alpha sorry, it should be capital F, fyk. And yk belongs to C. We use here. So this could be, so we can have this could be less than 0. This should be less than, give Give me 1 minute. Let me something.
What are you trying to prove? The convergence of covalent extragradient method?
Yeah, first we need to prove this sequence is phasor monotone
For the extragradient?
for this extra gradient.
It will be useful for our next steps, for example, Circumcenter, because we can.
Yeah, because in the analysis of these computations, we will see that we will see that this point xk plus 1 could be infeasible.
Okay.
Could be infeasible, and this point must be feasible, but may not be the projection. For example, this yk can be a little bit far away from the exact projection, but the yk cannot be outside. It could be inside somewhere close to the exact projection. So, yeah, this is why I want to analyze the proofs here, because
You are looking at Kopolevich method.
yeah. Yeah, because this gives us the interpretations why they propose this kind of horizon.
Show me horizon proposal.
Sorry. Yeah, this is Kopolevich. Yeah, this is another modification of the Kopolevich method. Just 1 second here.
Excuse me.
In the first modification, the first step is the A is operator. The first step here is the same. But the second step is just the use the projections to some half space. Half space is defined by this. There is a picture of this one. You see, this is called subgradient extragradient method. You see the x case is here, is a projection of this hyperplane, half space. But this half space is just separating the feasible set C and this point, and this point.
Let me look again at their method.
This one, yeah.
5 is sensor and Reich.
Yeah.
And who is epsilon k? What's epsilon k?
Epsilon.
Epsilon, yeah.
In the hyperplane.
The hyperplane.
Ah, sorry. This epsilon k could be 0 and should be positive. Should be positive and approaches 0.
Okay.
Of course, it could be 0. You can choose 0. And
The operator A is F.
F, sorry, A is F.
In the second step of the extragradient, they do the projection in a hyperplane.
Yeah,
This is the method.
yeah, this is one. They just use the projection to a hyperplane instead of exact projection to the feasible site.
Okay.
This is why I said in the extragradient method, this step, this point could be infeasible.
Okay.
You can see it from the proof.
Okay.
Okay, and but let's go ahead. And so you see this method, they project to this hyperplane. This hyperplane, in this case, the epsilon k equals 0. So this hyperplane hk, which tangent to the yk. Actually, we can also choose some other hyperplanes separating the point xk minus this tau f yk some other hyperplanes which not necessary to tangent here, but it's not so different. And sorry, I need to go back. And this method up to this method, I think is somehow the best modification of Kovalevich method, because in this method they only requires one projection to say, and 1 times of the operator. You use only 1 times of the f to calculate the value of 2xk minus xk minus 1, and 1 projections. You see, in Kovalevich method, you use 2 times of f. You need to calculate f, xk, and fy.
But how you define how you find that some method is better than other? How you determine?
Usually, I say the first assumptions. If you have weaker assumptions,
Okay.
it's good. Second,
But these and Kovalevich have the same assumption.
this one,
Yeah,
the second one,
yeah.
they have the same assumption.
So why is one is better than the other?
Because in each iterations, yeah, maybe it's not, but theoretically, I mean, from the iterations, it looks good. Because
but theoretically, you must look at
the numerical experiment is also better than Kovalevich.
This one.
In his paper, he compared with this method with subgradient, extragradient method.
What's subgradient, extragradient? Well,
It's this. This paper is in 2015. He compared his method.
yeah, but we are talking about Kovalevich.
Uh-huh.
You say that this is better than Kovalevich.
Uh-huh.
Why?
They have a numerical experiment.
They test this method against Kovalevich.
Yeah.
Has you done some numerical experiments?
I didn't do it yet, but I read their numerical experiment. They compared this method with this one, with the original Kovalevich and your method, and your method with Soldov.
Yeah, and their method is better.
It's the best, but not too much different.
No, I think you must check. Results must be reproducible.
Uh-huh.
So you must write a very simple code to compare.
Okay,
And
okay.
what do you compare? Number of projections and number of evaluations.
Evaluations, yeah, yeah.
And which kind of operator you will use to do this. Yeah, because if you use strongly convex, strongly monotone, is something. But if you use just monotone, like 90-degree rotation,
Yeah.
then you have a bad case.
Okay, okay.
So you must use a grain of salt.
Yeah, I will do the numerical
The
means
question
later.
is, what's the follow-up of this paper?
What's the
The follow-up.
follow-up?
Yeah, follow-up. If they propose a method and is more efficient, then that's natural that there will be some follow-up and people will verify that the results and so
This
on.
is interesting. When I put the name of this paper by this guy, I don't know how, this guy is from Ukraine. I put this from Ukraine.
Ukraine, okay.
Yeah, Ukraine. I put his papers in the graph, which can show the connections with this paper. No other fellowships comes out. Only study the strong convergence and the weak convergence of this method.
Yeah, but you must look at how you might look at MathCnet. Now it's not operating. Look at how you say that. Look at Web of Science or Scopus. See who are citing this work.
Okay, I will check it. There, I will check it again.
And do some numerical experiments.
I will do it. I will do it recently. I will compare this one and.
Choose an operator which is not a gradient of a function. Instead of that, you can put the gradient of position. For example, the gradient of a
Let's
function.
try a 90-degree rotation,
Okay, okay.
which is a bad operator, and you can do near 2 and put a 0, put the solution on the boundary, and also is a 0 of the operator, so you have some degeneration.
Okay, okay. But by the way, can you say that again? The rotation I know. And the operators is the rotation,
90-degree.
okay?
Yeah.
And the solution is, but the solution is 0.
Yeah. So devise a convex set which contains 0 in its boundary.
In the boundary.
Yeah. And very asymmetric ellipsoid, which
Which the solution is in the boundary.
yeah.
Portanto, por exemplo.
Like this could be. This is a ellipsoid.
Yeah, but tilt a little bit and
Not okay. Could be like this, okay?
tilt a little bit. Okay.
Like this.
No, tilt it.
What is tilted?
Tilt
Make a rotation.
yeah. Make a small rotation.
Make a small rotation.
Yeah. I suppose that.
Something like
yeah,
this.
something like that. Yeah.
Okay. So the feasible, this is a feasible set C. It's an ellipsoid with this is in the on the boundary.
Yeah.
The operator is this.
This is the dimension x, y. You can have a lot of copies of R2.
Okay.
In each one you put the rotation and something.
Okay, okay. I will test this.
You know, or you add a number. Yeah. And in some of the problems the solution is in the interior, so you have infeasible sets. Yeah.
Okay, okay. I will test this.
We can discuss some examples. And test these methods.
Okay. No, they didn't test these examples. They test, I don't remember, but they didn't test this bad. This is very bad example. Not good operators, this. Okay, so, yeah, up to now,
You see, they proved the convergence rate is better than Kopolevich.
they didn't prove any complexity.
Convergence rate.
No. But it's very interesting. Both in these two papers, they didn't prove the convergence rate.
Yeah, because classically, what was used was convergence rate in the case of strongly monotone operator. Now we have also complexity, but also test dynamics and do your own. Choose your own example.
Okay, okay. By the way, Professor, I remember all this method. I mean, when we use the projection to solve the variational equality, the velocity cannot be better than linear, right?
Excuse me?
The best result is linear for all these projection methods.
Yeah.
I think maybe this is why the reason people don't like to discuss the complexity of these things. Complexity makes difference. But the convergence rate.
In the past, before people began to be concerned about complexity, what they thought, what was studied was convergence rate in the case of a regular problem. Okay.
Okay.
And it's a natural question, but. Yeah, test this method when there is no.
Okay.
When there is no when all the space is yeah, send me this slide and I would like to check. Yeah, but it's a good idea to make your own experiments.
Okay. Okay.
And if their method is better, and why is it, and try to derive additional results about their method.
Okay, I will do it. I will do it recently because I just almost finished the proof of my work, and the next step is numerical result. I will do it in MATLAB. I think Luis Rafael will do it in Julia.
Which work are you talking about?
I'm talking about because we will also compare this with our Circumcenter method, with this and with this, I think. Okay, so yeah, this is a subgradient and extragradient method. Yeah, okay. So as I mentioned before, this point must be feasible, but it is not necessary to be the exact projection. So we can find some point close to this exact projection, but feasible. So that's why they use the feasible inexact projection here. So this is a definition. Actually, if this equals 0, this is the exact projection. So it is a good way to interpret this. We just eliminate this norm squares here. So we have the this inequality with 0 here, with some epsilon here. The epsilon is some tolerance of the errors of the inexact projection. So with this definition, okay, this is some properties of the inexact feasible projections. This you can derive them from the definition directly. Actually, this is also a kind of projection theorem. So I don't. Yeah. Okay. So if we use inexact feasible projections, we can have some equivalent statement of characteristics of solution of variational inequality. So the followings are equivalent. So if XA is a solution of the variational inequality problem, which also means the XK is belongs to the inexact projections for all X belongs to, there is table here, 0 to the infinity. This is somehow like the optimal condition for the constraint optimization. I remember in the sort of the book they have something like this. And okay, the last one is the tool to prove the convergence of their method. Okay, so yeah, this is they call the extragradient inexact projection method. The only difference is they use the inexact projection here with the tolerance gamma k. The gamma k is the same in both steps. And we have some assumptions. Because the step size alpha is constant, so the alpha is related to the Lipschitz constant and also the upper bound of the arrows of the inexact projections. But there is problems, not problems. There is a point here. They call these arrows gamma k relative arrows. But we can see this alpha k. Okay, this alpha k is the upper bound of this gamma k times the norm of fxk. But we need to require this alpha k is summable. Since it is summable, it approaches 0. So this gamma k times the fxk squares approaches 0. But if this fk, the value of fxk squares not approach 0, which means their gamma k will be 0. So this arrow's gamma k also depends on the fxk. I don't know if the xk approaches a solution set, approaches x star, if this fxk will approach 0 or no.
No, you require that this inequality holds.
Yeah, we require this inequality hold.
You do not prove that it holds. You require it to hold.
We require it holds. This is from the Olizon's paper. They call it relative arrow, but they require this hold. And they require the alpha k is summable. But in this case, the alpha k, the gamma k may approach 0 if this fxk not approaches 0. And this step size is not new because it's almost similar to the step size in the extragradient method. Okay, so yeah, the proof first they have this kind of like Figure monotone result. They prove this if xk star is a solution. They have something like this. And with this, they prove the convergence if the alpha k is less than some constant related with the upper bound of the arrow of the projection and the Lipschitz constant. Then the whole sequence converges to a solution of the variational inequality problem. Yeah, they also proposed another version. In this case, they do not require the assumption of Lipschitz constant. It's like your method with Soldov. First, we have the yk. Yk belongs to the inexact feasible projection of xk minus beta k fxk. I will draw a picture here. This is a feasible set C. We have xk here, and first we have a point xk minus alpha f. They use beta k here, xk. This is an exact projection, but somehow we choose the inexact projection. This yk belongs to pc gamma k xk minus alpha, no, beta k fxk. Okay, so they have a yk here. Then what they did is they do the line search along this segment, along this segment. But their research is a little different from yours, Professor. Here, they request this. The ik is a minimum of which satisfies this inequality holds. I have a doubt here.
Excuse me. Well, you are doing a convex combination of 2 points?
Yeah. So the dk should be somehow in this line segment. For example, zk is here. This point is zk.
I don't see what's the difference. Besides sigma, that's less than 1, I guess. I see.
It's different.
I see. Okay.
But to be honest, I didn't interpret this very well. I understand the line search in your paper because that guarantees the separating hyperplane. Yeah.
Excuse me, let me see something.
Yeah.
What do you assume about hold?
This is a beta head.
Hold.
Hold. What? Where?
In the line search.
Here. Yeah.
Oh, yes,
This row. What is this?
Row.
Yeah.
Yeah, it's between 0 and 1.
It's another thing. There's
Yeah.
another criterion.
Yeah, another criteria. But I have a dot here because why I have a dot here? You see, let's go to the next step, okay? The next step is we have xk plus 1, and we calculate the xk plus 1 is the inexact feasible projection of this point. I will draw a picture here.
Where is Z in this project?
This should be z, sorry.
Okay.
This should be z. So we have,
What do you know about the sign of f of xk, y minus xk? What do you know about the sign of this inner product?
this one,
At the right.
this one.
Yeah. Is this bigger than 0, smaller than 0?
No, I don't know. I don't know.
But they don't.
This is why I said here. Give me 1 second. If we times minus, it is positive. I think so. Because yesterday when I read this paper again, I have some doubt about this lens search. Because in some situations, this lens search doesn't make any sense.
Yeah, you must see if it's always satisfied for some I bigger. And
They proved that this is well defined. And that proof is okay, I checked. But in some sense, I mean, this inequality holds for any I. For any I. And okay, let me go ahead because they use something the same to your paper, professor. So this is xk. We go somewhere like here. This point we call it xk minus lambda k fzk. And then this is the exact projection, but we use the inexact projection here. So this is k plus 1. How did they calculate this? Sorry, how did they calculate this lambda k? The lambda k is equals to this. Where did this came from? They said this lambda k is a projection. So we have zk here. We can define a half space which crossing this zk. We call it hk. It defines in the same way with the one in your paper. The norm vector is also fzk. It is defined in the same way as in your paper with Soldorf. So the lambda k they said is they just calculate the projection of xk to
the half space and then project.
yeah, then project. This is how did they get the lambda k here. But they said this hk separating the xk and the solution side with this lens search. But I have doubt about that. They didn't prove this.
No.
I didn't
They didn't prove. They proved convergence of the method.
I think, yeah, I checked, it's okay. Until yesterday, I remember I saw something where I read your paper again, I check your paper, your hyperplane exactly separate with your lens search. But I realized this lens search is different. But they still said the hyperplane, because this hyperplane defined by zk. zk is related to this lens search. So somehow this hyperplane is related with this ik here. with this AK here. They said this hyperplane separates this XK and the solution set. But I have doubt about this. I have a doubt about this. Another thing I need to say, this method here is more like your paper with Solodov, not the Kopelevich. Am I right? This is more like yours.
Yeah, it seems so.
Yeah. But they call it extragradient, so I don't agree too much.
Well, it's extragradient because you ZK. Yeah, because he using the last line is ZK, it's not YK.
Yeah, ZK.
Well, you are updating, you are projecting onto a house space generated by a point which is not XK. It's not, it's not XK.
Yeah.
Is ZK. So exactly great.
The only thing here in this method and your method is they use the proxy. No, they use the inexact projection here.
Okay.
They use inexact projection here. Yeah, this method converges. They will converge to a solution, and
maybe it's more similar what I have done with Alfredo. What I have done with Alfredo, and we did not project the interception.
I know.
I think we projected in one and then in the other, but we used the Armijo as Armijo criteria.
Okay.
Look at my paper.
Okay, I didn't read that paper. Sorry.
Yeah, read my paper with Alfredo using.
Okay. Yeah, because I know both of these two kind of line search that didn't require a lot of projections in backtracking.
Yeah, that was
The key point of your paper with Usum, yeah.
We use it and with Solodov also because we use the same line search.
The same line search?
Yeah.
I only know that in your paper with Solodov, you have a good interpretation of that hyperplane.
Yeah, in my paper with Solodov, we project onto the intersection. I think in my paper with Alfredo, we project onto the hyperplane and then project in the space, on this feasible set.
Okay, I will check that. So up to now, this is two kind of algorithms with two kind of inexact projections. First, by Fukushima and Junior and Alfredo, they used the projection to some half space, which is not feasible. And in this slide, the method by Olison, they use the inexact projection but feasible because the framework is based on the extragradient or based on your.
This is the Olison.
Yeah, this is Olison.
And this the inexact projection is something related with the inexact solution of the proximal equation for the resolvent of and the subdifferential of the indicator set.
Yeah, by the way, I think it's also related with if I read the gap function of the variational inequality, it has some relation with that, yeah.
Yeah.
That gap function by Fukushima.
Yeah, but the regularized gap of Fukushima when a parameter is equal 1/2 of 1, I can remember, that gives a merit function that we need in the hybrid proximal extragradient method.
Really?
Yeah.
Oh, okay. That sounds nice.
You can interpret as an epsilon and as an error. Yeah.
So it's also a kind of HPE, yeah, special of HPE.
Maybe, but I talk about merit function from Fukushima.
Okay.
I don't know how we use it.
Okay. I will read it because recently I read something about that. By the way, I just need to mention a little bit. I don't know whether Max was watching this. Yeah, the first version of Olison's.
Where the Horizon and Max published their work?
They work in co-op. July. Because this year. Because I wanted to do something very similar to Max and I want to do something almost the same as this, but we don't know they publish this.
Because of the time, you can go to your.
Okay, okay.
If you don't mind, of course. Because we have 2 slides before the Circumcenter. Yes.
Yeah, I will say very fast, okay? But just 1 minute, just 1 second in this slide. This method is a special case of HPE. It's a special case of the proximal point with relative arrows. Just to see that I don't know who proved this before, but Max proved this, and he told me that it's a special case of HPE. Okay, because of time, I just go to here. So this is Circumcenter because everyone knows the Circumcenter here. So yeah, I just introduce the method. Here is the Circumcenter for the variational inequality with paramonotone. The only difference is we use the Circumcenter operator here. But this TSD Circumcenter operator is with proximate projections, which means when we use the projection, we project to half space related to each convex set. Of course, in this case, we consider the problems like this. We want to find the x star set such that fx x star x minus x star is greater than 0, but x belongs to the intersection of ci, I from 1 to m. So we consider.
The slides previous, what did you put in the slide previous of that?
The problem. Which problem are you?
Okay, this problem that you are writing in the blackboard.
Yeah, this problem. The only difference is the solution side is not C. It's the intersection of many convex sets.
Okay.
And we use, here I just want to say, we use the TSD. It's not exact projection version of Circumcenter. It's the Circumcenter of with inexact projection, which means in each step the projection is in the half space separating the set Ci. But this only works for the paramonotone variational inequality. So next step, I will do numerical experiments with this method and with the method of Usum and Unier, Fukushima. And another version is this, we call it Circumcenter extragradient method. First, we also use the inexact projection, inexact feasible projection with epsilon k here. So the framework is also based on the extragradient, and with some line search, which is this lambda k equals this lambda k equals to the gamma LMK. MK is the smallest non-integral, satisfies this. This is somehow another kind of line search. Not another kind, another formula of the line search. And the second step, we do the we do the Circumcenter, but with approximate projections. So in 2 kind of versions, we just use the Circumcenter to accelerate the feasibility part of the problems. Yeah.
For example, if you take the horizontal, or for example, Solodov algorithm, and in each step that you have to do a projection, you use the Circumcenter projection.
It depends. It depends. Sometimes you can use Circumcenter. Because when you use the Circumcenter operators, I will show you here. This is the definition of Circumcenter originally. When you use Circumcenters, the point will be infeasible. It depends on if it's the algorithms from Binar, from anyone else. If it requires feasible. You can't. If that's why.
So the main idea you are changing the projection by the circumcenter operator.
Yeah.
Okay, nice.
Yeah, it's the idea is very, very, very simple. It didn't. You see, in first step we didn't use circumcenter here, because it must be feasible. But in the second step we can use the circumcenter here, because the second point doesn't to be feasible. And here we use the circumcenter with approximate projection.
But you are working in PRI space.
No, we are working in the proof requires the product space, actually.
But the circumcenter is with respect to which projections? Yeah.
We work in Rn, not in the product space, but the proof requires product space.
Yeah, but your set C is intersection of CI.
Intersection of CI.
And how you project onto the intersection of CI?
Yeah, I have some ideas here.
But now the structure of CI is immaterial here, because you are projecting onto C.
See. This is a problem in the beginning. Yeah, this is, in our version, the epsilon k is a constant, is a sequence which approaches 0. It means in the beginning, this what you said is a big problem of this thing. You need to, in the first step, somehow you need the projection into the intersection.
Yeah, but regardless of this, you are talking to circumcenter with respect to which half space, which reflecting points. We are reflecting onto what? Because we are doing two reflections.
Yeah. So the problem is here, okay?
Okay.
The first reflections is respect to, we call S. S is the product space of S1, Sm. Each S contains Ci. For example, Ci is contained in Si. This Si is a separating side of each side. Okay. Well, first we project to this S, and it looks like in the product space, but in the practical calculation, it is not in product space, it's in Rn, it's in the original space. The second side is U. U is the diagonal space, X, and X belongs to the Rn.
I don't know what's practical. You are writing the S as a Cartesian product.
Yeah.
So if you do reflections, you are doing reflections in this space.
Actually, the circumcenter is a special case of the simultaneous projection method with a very specific convex combination. Not convex, combination. So you can do this projection. Actually, in the practical situation, you do the reflection to each one simultaneously. And then you have you need to calculate the circumcenter. So actually, no, not actually. You do it simultaneously, so not everything is in the original space. But in the when you prove the convergence, you need this.
But when you operate, you do the projection on each one.
Each one.
Okay.
Each one, exactly. What you said is totally correct. This is somehow the biggest problem of this thing. People will ask, how do you calculate the first projection? Yeah, it is a kind of projection into intersection. What you said is totally correct. We cannot solve this. We need this, in the first step, we need to find some point, at least an inexact feasible projection of X to the intersection. That's why I want to introduce this PC epsilon k here. It makes a little bit better, not too much better. This is still a big problem. But what I want to say is, our convergence result, our convergence just requires this epsilon k goes 0. but in the beginning it could be somehow a little large. So in the beginning, in the first few steps, we do not need to calculate projections. We can just find a feasible point in the intersection. For example,
you must define what TSD of a point means.
Where?
What's the meaning of this operator, TSD?
In the previous slide.
Yeah, I know.
Yeah, let me see. Show the previous slide.
Yes.
This is circumcenter, respect to set A and B.
Okay.
The S is defined in this way. It's a product of S1 to Sm, and each S is a separating set of each Ci.
Okay. And this is one of the sets. And the other set?
The other set is U, is a diagonal space. Each exponent is the same. This is D. This is capital D. This is capital S, both face S. This is a big problem of my ideas now. We need the first step one, yeah, step one, because this say here is intersection of many sets. Because people can ask, if you know how to project into the intersection, why would you use circumcenter? But it accelerates, because in the second step you do not need a feasible point anymore. It's not a very nice idea, I need to say. By the way, so I wonder that
If you apply the Circumcenter in the previous step, does not work off because you need the
because this is based on the extragradient. In extragradient, the first point should be feasible. At least you need one feasible. Actually, the first point should be feasible. But if you use circumcenter in two steps, for example, you use circumcenter here in the first step, you lost the feasibility.
Okay, yes.
That this doesn't work.
But the idea of Circumcenter for convex feasibility is to achieve a feasible point after
Iteration.
apply the operator.
Yeah. But in this first step, since the framework is based on the Kopelevich method, we cannot solve this difficulty now. In other words, Professor, up to now, I think there is no method use approximate projections to solve the variational inequality with monotone operators. You see, the now we want to solve a variational inequality. The operator is monotone. All the method requires at least one feasible point. Can people find a method which all the sequence is infeasible, but you can approach the solution? Up to now, I think there is not.
You are thinking about infeasible projections.
Infeasible projections.
So you were thinking about projecting onto
Half space.
half space.
Because the method I talked before, like Fukushima, U-sums method, you see this, this U-sums method, the operator is paramonotone. But for the monotone, all this method, the sequence is infeasible. But for the monotone, up to now, I didn't see any method they generated the sequence infeasible, which means you can only use the projection to half space.
I'm sorry.
No. So I'm still thinking this problem of.
It depends. If the function is, if the sets are given by are level sets on the convex functions, then you are good to go.
Really?
Yeah.
It's possible.
Yeah, that exists.
If for example, if the C is the set level, the level set of a function, convex function, you can only use the projection to half space, separating half space, solve the variational equality. Okay, do you know the name of the paper?
Look at Monteiro, Schweiter, and Michael paper. And now Michael Alves.
Montello's with Michael with you, or only Montello with Michael?
Michael, Alves, which is Michael, Monteiro, and me.
Okay, I will check it for the variational equality.
It's more general.
Okay. I think we can stop the recording now, yeah? Olá, ficha agora, tá bom? And